Hello, I'm Dr. Beth Pedney, and in this video I'd like to walk you through probability and more specifically how to use contingency tables. So let's start first by talking about what is probability. Probability is the likelihood that a given event will actually occur. This is very useful in terms of quality when we look at inspections. We want to know the probability that we're going to be able to find a defect. When we think about this in terms of our internal processes within our organization, we can capture the probability that we will have a defect by looking at how much variation there is within our processes, and then the likelihood that we're going to have a product that's outside of our specification limits. In addition, we can use this in terms of incoming inspection because we can't afford to inspect 100%. So typically what we're doing with incoming inspection is taking a lot of material, and out of that lot of material we're going to sample so many parts and inspect those. And then if they're good, we're going to assume that the rest of the lot is good. Or if it's bad, based on the rules that we've set up within our organization, we might select another sample of products to see if those products also contain any defects. We're going to represent the probability of a ratio that a specific event A can occur in ways out of n equally possible ways. So the probability of A occurring equals to m divided by n. So before we get started, let's talk about a few of the basic probability terms. The first is an experiment. An experiment is a clearly defined procedure that results in observations. When we have a single performance of an experiment, that's called a trial, and each trial results in an outcome, which is typically referred to as an observation. Now, for what we're talking about in this video, the experiments that we're dealing with are called random experiments, in that the outcome in any one trial of the experiment cannot be predicted with certainty. When we talk about the set of all possible outcomes of a random experiment, that is referred to as a sample space, and it's typically denoted by an S. And then each element of the sample space is called a sample point. And then an event is a subset of the sample space such that all elements in it follow a common rule. When we talk about a simple event, that's where one event takes place. For example, we could have a single toss of a fair coin. A compound event is when two or more events take place. For example, you could roll a fair die 3 times. Before we get into contingency tables, there are a few important rules of probability that we need to discuss. The first is a complementary rule, and it states that the probability that event A will occur is 1 minus the probability that event A does not occur. The next is the addition rule of probability. And with the addition rule, it states that when two events A and B are mutually exclusive, the probability that A or B will occur is the sum of the probability of each event. In other words, the probability of A or B happening equals the probability of A plus the probability of B. Now, if A and B are not mutually exclusive, then this equation changes slightly. When two events A and B are not mutually exclusive, then the probability that A or B will occur is now the probability of A or B equals to the probability of A plus the probability of B minus the probability of A and B. Since they're not mutually exclusive, there's overlap in the probabilities. And essentially by adding the probability of A plus the probability of B, we are now capturing that space of overlap twice. Therefore, we need to subtract that area of overlap by subtracting the probability of A and B. Now a few more terms. The symbol that looks like a U means or. So if we're talking about the probability of A or B. And the symbol that looks like an upside down U means and. And that's used when we're talking about the probability of event A and B occurring. And the final term is mutually exclusive. Two events A and B are said to be mutually exclusive if both events cannot occur at the same time. For example, if we go out and think about buying a shirt, shirts typically come in small, medium, large, extra large, and so on. If we buy a shirt, it can't be small and extra large. It's one or the other. However, if we add another element into this, like the color of the shirt, a shirt could be blue and small or blue and large, for example. But when we just talk about the size of the shirts, those are mutually exclusive. Conditional probability is used when we want to understand the probability of B occurring given that A already occurred. In other words, this is the probability of an event happening given that another event has already happened. And this is calculated as the probability of A given that B has already occurred equals to the probability of A and B divided by the probability of A. The next is the multiplication rule of probability. And we can rearrange the formula for conditional probabilities to get the equations for the multiplication rule. And in this sense, we could have the probability of A and B occurring equals to the probability of A times the probability that A will occur given that B has already occurred. So let's take a look at a few examples so we can see how to put these equations into use. So first, let's look at what is the probability of tossing a die and observing the number 5. So we're looking for the probability that we're going to get a 5. If we're talking about a fair die, there are 6 sides, and one side has the 5 on it. And so that equals to 1 divided by 6. So now let's take a look at the probability that at least one of 3 tosses will be a 5. So now we're looking at the probability of 3 different possibilities and 5 occurring on any of those 3 tosses. So we're looking for the probability that 5 will occur on the first roll, or 5 will occur on the second roll, or 5 will occur on the third roll. So that's equal to 1/6 plus 1/6 plus 1/6. We can also look at determining the probability that you will roll a 2 and then a 3. So in this sense, we're looking at the probability of rolling a 2 and then rolling a 3. So that equals to the probability of rolling a 2 the first time, which is 1/6, times the probability of rolling a 3 on the second roll. And that's equal to 1/6 times 1/6, which equals to 1/36. So now that we've discussed some of the basics of probability, let's take a look at how that applies with contingency tables. And contingency tables are a very effective way of arranging attribute data that we have to determine the relevant probabilities. Contingency tables contain count data that can then be analyzed to determine if 2 variables are independent or related. 2 events A and B are said to be independent if and only if the occurrence of B has no effect on the occurrence of A and vice versa. So in other words, the probability of B, given that A has already occurred, is equal to the probability of A. B has no effect on it. Likewise, the probability of A, given that B has already occurred, equals to the probability of B, because A has no impact on the probability of B. Now, if we talk about dependent, 2 events A and B are dependent if and only if the occurrence of B has an effect on the occurrence of A or vice versa. So when we look at the previous equations now, these are not equal to each other. So the probability of B occurring, given that A has already occurred, is not equal to the probability of A, because we have to take B into account, since it has an effect on the probability of A. And likewise, the probability of A occurring, given that B has already occurred, is not equal to the probability of B. Again here, because the probability of B is impacted by the probability of A. So now let's take a look at a contingency table example to see how we can take all of the different rules of probability into account by using the tabular format. So let's look at an example with a flower shop that has roses, tulips, lilies, and peonies, and they're available in pink, white, and orange. So in this table, we have all of the colors in the first column, and in the top row, we have the different types of flowers. In the far right-hand column, we have the totals for the different colors of flowers, and in the bottom row, we have the totals for the different types of flowers. And in total, we have 700 different flowers available. Using this information, we can determine the relevant probabilities. So if we consider the probability that a flower chosen at random is a rose, we're looking for the probability of a rose. Looking at our contingency table, we have 270 roses out of a total of 700 flowers. Therefore, our probability is 270 out of 700. We can also determine the probability that a flower chosen at random is orange. So here we're looking for the probability that the flower is orange. Looking at our contingency table, we can see that we have 193 orange flowers out of the total of 700 flowers. Therefore, the probability that a flower chosen at random is orange is equal to 193 out of 700. Now let's take a look at how we could use some of the more advanced tools that we just discussed in terms of determining probabilities. So first, let's look at the probability that a flower chosen at random is a pink tulip. For this, we're looking for the probability that the flower is pink and a tulip. Looking at our contingency table, we have 78 pink tulips out of the 700 total flowers. So our probability then is equal to 78 out of 700. We can also determine the probability that a flower chosen at random is white or a peony. So let's first look at the probability that a flower would be white. Based on the contingency table, we have 182 white flowers out of the 700 total flowers. And so that gives us the probability that the flower is white is 182 out of 700. So now let's look at the probability that the flower would be a peony. Based on our contingency table, we have 131 peonies out of 700 flowers. And so now we're adding in the probability that it's a peony of 131 out of 700. So now if we go back and look at mutually exclusive events, we've essentially double counted where the flowers could be a white peony. And therefore we now have to subtract that overlap so we're not double counting it. Looking back at the contingency table, we have 54 white peonies out of the 700 flowers. And now we're going to subtract the 54 out of 700. And therefore the probability that the flower is white or a peony is 259 out of 700. I hope you found this video useful in the understanding of basic probability and how contingency tables can be used as a way to arrange attribute data to determine relevant probabilities. I wish you the best of luck on your process improvements.